We have seen two problems so far where we have used the two-pointed technique to reduce the complexity of the solution. The first one was the pair sum problem, and then we looked at this problem of merging two sorted lists. Now let's look at something quite interesting, which looks a little bit more complicated than the previous two. I call this a carpet area problem, but in fact, this problem I have adapted from a very famous, let's say, competitive programming problem, which is called container with most water. So the maths of this, the logic of this is exactly the same as this container with most water. But I found that the physical interpretation of this, relating to the real world, I thought this is a little bit, hard to sort of believe, right? So I kind of changed that water to a carpet. So the idea here is like this, that look, let's say we have parallel lines marked on the floor at a fixed distance from each other. These lines are of different lengths, and these lengths are available to us in a list. So now the task for us is to find the area of the largest rectangular carpet that we can fit between these lines so that no edge of the carpet is outside the vertical lines. Now, a lot of words. So let's try to sort of understand this with some pictures, because pictures will make it very clear. So here the problem is like this, right? So we have these lines marked on the floor. So let's say 6, 4, 5. These lengths of these lines, it could be any units, meters, maybe feet or whatever. So these lengths are available to us in a list. So we have the 6, 4, 5, and so on. Each of these lines are a separation of 1 unit. So maybe 1 meter or something like that. Yeah. Now with these lines available to me, now what I'm interested in, what is the largest carpet that I can fit inside this, let's say, structure, so that the carpet is nicely bounded by any of the lines that it's touching. So for example, if I want to, place, let's say, a carpet between these two lines, 6 and 4, well, the carpet can be only of this size, because, the carpet has to be well bounded. So I can, for example, put a carpet of the size of the area 4 unit square, because, this is 4. I can similarly put a carpet of, let's say, 15 units between this line and this line. I can put a carpet area of, let's say, 6 units between these two lines, because 8 and 6, sorry, 5 units, sorry, 8 and 5, and so on. So basically, I look at any two lines and I see what's the largest carpet that I can fit. Let's take a few more examples. For example, here I can put a 16 unit between these two. I can put a 30 between, let's say, 5 and 6, because 5 and 6. The reason I'm having to put it this way is because anywhere where the edge protrudes out would be seen as invalid. So for example, in between these two lines, remember this was, let's see, this was 6 and 4. I mean, these diagrams are not to scale, but you get the idea. So 6 and 4, or maybe 6 and 2, whatever. I cannot put this area here because this edge is protruding out. Likewise, between these two, let's say, lines, I cannot put this, because now notice this edge is protruding out. So basically the problem statement is, what is the largest such area between two lines, and which are these two lines, right? So I want to put a carpet. So for example, here 16 is less than 30, but is this the largest, right? So given, let's say, a lot of lines, I want to basically figure out what is the largest carpet that I can fit without the carpet protruding anywhere, right? So basically, like I said, this problem is adapted from I mean, the story of this problem, you can say, is adapted from this container with most water. So the idea there is that instead of carpet, they talk about container. But I thought having a rigid structure like a carpet, makes it a little bit more clear, because otherwise lots of questions arise as to why water can't go to certain places. Yeah? So this is the carpet rigid. For example, I can place this. Question is, which is the largest of all this? So that's the problem we're going to solve. Let's analyze this a little bit more carefully. Basically, the metric of interest is the area that is bounded by any two lines. So, for example, JJ and KK are my two indices. Remember, these lengths are available to me as a list. So, I look at LJJ, I look at LKK. The metric of interest that I have is, look, between these two lines, what is the area that is bounded? And think about it, that area is going to be given by minimum of these two, minimum of LJJ, LKK. So, whichever is the smaller length, multiplied by the absolute value of kk minus jj. So now absolute value basically is the positive part of the, let's say, the difference. So let's take some examples. For example, in, we just saw this. Let's take this as a reference. Basically, between, let's say, lines 3 and line 6, so the horizontal gap is 3. Remember, I'm going to look at the minimum of the two. Minimum is 5, so that's 5 times 3, 15. Likewise, between these two, horizontal gap is 1, so abs of 0 minus 1, or say just 1 minus 0, whichever is bigger and smaller, that becomes absolute value. So, minimum gap is 1. Sorry, the horizontal gap is 1. the vertical distance has to be 4 because that's the minimum of these two. So that's going to be 4 units. So this is basically between any two lines, any two lines, between any two lines, let's say JJ and KK, whose lengths are LJJ and LKK respectively. We got to find out, the area. And what we are interested in is that pair of LJJ, LKK, or let's say JJ and KK, where this area maximizes. So that's what we are really interested in. So if we state this a little bit, let's say more precisely, basically we are looking for long lines that are also far from each other. And in a more precise manner, we are looking for two lines at JJ and KK with lengths LJJ and LKK respectively, so that minimum of LJJ LKK times absolute value of KK minus JJ is the highest amongst all possible values of JJ and KK. Now that's once we state the problem this way, then story really doesn't matter. It could be water, it could be carpet, but like I said, carpet makes it more, let's say, relatable to the real world, right? So I hope the problem statement is clear to you. Think about it. These pictures are quite illustrative. We are going to look at how do we solve this, and in fact, since we're talking of two-pointer solutions, we'll see that two-pointer technique will in fact help us reduce the complexity of this down in a significant manner. We'll again come back from a n square complexity to n, so a linear complexity. We'll discuss this in the coming videos, but I hope do look at our website www.ybyte.in, because we always approach problems in a systematic step-by-step manner, explain them in clear terms, and we have a lot of fun building algorithms and programming. Take care. Thank you so much. Bye bye.